All right, CNT 140, we're working on Chapter 5. We're not digging into the section specifically on fiber. So hopefully some of this is a review of things you looked at in 120. It might fill a couple gaps in for you as well. So we have to remember the fiber itself. This glass strand, if you will, is actually made up of two parts. There's a core and a cladding. The core is super clear glass, and the cladding around it is also clear, but it's purposely designed to be not quite as clear, so it will actually reflect or bend the light back into the core of the fiber. That's how it's constructed. That's how it's built. So if I were to actually cut a cross section of a fiber, if we actually take a piece of fiber and cut it apart and look at the parts, this is what you're typically going to find. Now, this is typically the kind of fiber, multi-mode fiber, that you'd find maybe in our land backbone in a building. So I'm using this sample for you. I cut away the outside jacket. In there I'll find a strength fiber. Those are typically like Kevlar strands. They're there for strength. They're there as you go to pull on the fiber. That is taking the tension versus the glass fiber in the middle. Once I cut away the strength fibers, I'll find this right here. It almost looks like another cable jacket, but it's the buffer. It's like the insulation around the actual fiber strand. Then once I get to the fiber strand, I will actually find the cladding and the core. So that right there, if I were to look at the end of the fiber, I would see that. If I were to look at the end of the fiber under a microscope, I will see the core and the cladding, which again, we will do that later this semester when we focus a little bit more on fiber optic. Typical fiber connections that we're going to work with are going to be two strands, one for sending and one for receiving. So you end up seeing fiber connections like so. One send, one receive. Here's a whole cable. You can see the two fibers to literally make the single connection between two switches. One is sending, one is receiving. The fiber itself is characterized by the size of the core and the cladding, if you will. So if I take a look at multi-mode, single mode, there's two types of multi-mode I run into, step index and graded index, and there is single mode. Well, if I look at them from the side and I look at how the light is traveling through them, here's the differences I see. Now, before you get maybe stuck in an idea, what we're actually seeing is like one pulse of light representing a 1. Followed by this, there would be a space in the fiber with no light in that would be representing a 0, followed by another pulse of light representing a 1. So we're actually looking at like a single 1 going through the fiber. We're not looking at, 6 different signals moving through the fiber. These rays of light are one pulse representing a 1. Okay, so just before you get too sidetracked on what you're seeing here. Well, on a step index multimode fiber, this is your largest core diameter, 62.5. A pulse of light from typically an LED. The light rays, the modes of light, hence multi-mode, multiple rays of light. Multiple rays of light are bouncing down the fiber to make a light pulse to represent a binary 1. If I look at the multi-mode, it is actually bouncing down the fiber. The cladding is reflecting, almost like a mirror, reflecting the light back into the core, so it's going to bounce its way down the fiber. If I look at the next type of multi-mode, this is your graded index. It's the 50 to 125. The core is a little bit smaller. Here, the difference between the core and the cladding is a little more subtle. So as the light tries to leave the core, the cladding actually bends it back in. It refracts it back in. Instead of reflecting off of a mirror, it's going to bend the light back into the core. So you get a lot more gentle modes of light traveling down the fiber. Again, we're not looking at 5 signals here. We're looking at one pulse of light representing a 1, a binary 1, but it happens to be made up of multiple modes, multiple rays of light. Last but not least, the smallest fiber we have, single mode. This core down here is around 8 or 9, sometimes 10 microns in diameter. So we had 62.5, 50, and then we're down to like 9 microns in diameter. So this is a super small core. You can think of this as like a coffee stirrer straw, as opposed to one of these up here being a milkshake straw. Okay, so this super tiny like coffee stirrer straw, is the core is so small. I'm literally focusing the light in here as a laser light, and as it goes to travel down the fiber, this single mode of light, this single ray of light, the single mode of light is traveling down here. It has nowhere to go, so it's kind of coaxed to stay right in the middle and travel down the middle of the fiber. Hence single ray of light. So what I did here is I put the sizes of fiber next to it so you can see the 62.5 multi-mode, the 50 multi-mode, and the 9 single mode here. Okay, that's how we typically talk about fibers, by either the core to cladding relationship or ratio. So here's your multi-mode again, the step index 62.5 to 125. Here's your core to cladding. The graded index 50 to 125, core to cladding, and then the single mode 9 to 125. And you notice the cladding on all these stays the same, which helps with component manufacture, connectors and tools and devices and so forth. Okay, but the core keeps getting smaller. Here's kind of like a comparison if you were to look at, if I were to look at the fiber, if it were this big around. Now the actual fiber itself is the size of a human hair, okay? But if I were to, kind of scale it up so I could look at it, you see the multi-mode 62.5 is a nice big core. The 50 is a little smaller, and then that single mode is teeny tiny, okay? Teeny tiny. That's your teeny tiny single mode fiber. Multi-mode fiber is typically going to use like an LED light source, or VCSELs, vertical cavity surface emitting LED. Typically in the 850 nanometer light source range, it is a short wavelength, so it's going to go, I'm using air quotes here, short distance. Okay, that's one way to kind of sort some of this out. A shorter wavelength is going to go a shorter distance, so this is typically used for LANs. Multi-mode fibers are typically used for LAN environments. Meanwhile, your single mode fiber, we're typically dealing with a laser light source, and we're typically in the 1310 to 1550 nanometer wavelengths. So these being longer wavelengths are going to go longer distances. That's one way to kind of help sort these out. So we're now talking maybe campus connections or WAN connections, if you will, okay, with your single mode fiber. So most premise cabling that we would be dealing with in a LAN would be multi-mode fiber for our backbone connections. And again, we have some of these different sizes of fiber. For many years, the 62.5 125 was kind of the standard. That was primarily used in your premise cabling. So eventually it got standardized into calling it the OM1 fiber. And again, it was using the 850 nanometer laser light source used for gigabit and so forth. OM2 switched to using the 5125, that graded index fiber. That was then optimized for laser use, for actually laser source. So being able to do higher bandwidths, greater distances. In some cases, just higher bandwidths, maybe not as far, but higher bandwidths. Manufacturers then developed OM3 fiber, higher bandwidth, longer link capability. Now we're getting some longer distances. So now this is typically the fiber that gets used in LAN backbones today. And then OM4 fiber, 5125 again fiber, is in development to try to, again, increase the capabilities of bandwidths and distances of. To help kind of sort them out, I found a graphic here that shows you kind of like the timeline development, but also the color code of these guys. So back in the OM2, we had like your orange cabling. The OM3, we start getting your aqua cabling, then we get blue, and then we get green. Okay, so just as a kind of like maybe to sort them out in your brain. Now, I actually tried to compile all this into one chart for you, but it got kind of small. There was a chart in the book, and I took that and kind of redid it and tried to add some more info. So you can use this and zoom in, but what I ended up doing for you to help you out is on the next slide here, I put links to multi-mode fiber in general, fast Ethernet, gigabit, 10 gig, 25 gig, 40 gig, and 100 gig Ethernet. And if I open these sources up, it'll bring you to those Wikipedia pages that have this broken out in more detail for you. So if you ever need to look up any standards on the distances, capabilities, the wavelengths, etc. on a particular fiber, this will be a good resource page for you. These were all the things I was bookmarking to make that chart, and I decided to just put them in here to make it a good resource for you to use as you need. They're reminding us in this part of the chapter that most of our fiber connections are 2 strands, one to send, one to receive. So now the transceivers that we have are actually designed to be transmitters, receivers. Part of the optics are sending, the other part is receiving. And that across that fiber would need to be used. And they do a little side story here on some fiber, especially in fiber to the home, that single strand of fiber can actually do signals in both directions. Now you need special optics to do that, but you can have optics that will send and receive across a single strand of fiber. And that's the kind of thing you start getting in passive optical networks, fiber to the home kind of thing. The kind of stuff we're probably going to be dealing with in LAN environments is back here where I have 2 fibers, one to send and one to receive. And that's where the transceiver comes from. Part of the circuitry is transmitting, the other part is receiving. So the transmitter is taking the electrical input from a switch port, computer, etc., converting it into an optical signal, pulses of light, to send across the fiber. The light is then transmitted into the fiber through the connector and so forth. The other end of the cable then, there's going to be a receiver hooked up to it, and the light from that is going to hit the circuitry in there. You can almost think of that as like the sensor light on an if you have an outdoor light, if you have a light outside that kicks on at night, there's a little sensor on there, a little photocell in there, that if you go out and put your thumb over it in the middle of the day, the light turns on. Well, it's that kind of circuitry that's in there, obviously a lot more sensitive, but there's that kind of circuitry in there. When a pulse of light hits it, it is able to produce electrical charge and send electrical charge out, or basically a 1 out. So on the receiving end, on that receiver, there is circuitry there to take that pulse of light that hits it and turn it into a pulse of electricity, a 1, if you will. And that's what's actually built into these kinds of things right here. This SFP module that I would be plugging my fiber cables into, my fiber ports into, has that circuitry in here to receive here, so to speak, and send over here. And that's kind of where we would see that transceiver. The performance of a data link, we're going to do some testing later this semester on our fiber links that we have. So this is going to give us kind of a little heads up as to what's coming down the road. But you can actually measure the performance of the link with certain meters, but we're going to run into the performance of that link can be determined by the capabilities of your transceiver, your receiver optical power, and your receiver sending power. I can have high bit rates if, I think I say it over here, yeah, here we go. If I send too much power, the receiver amplifier saturates and distorts. If I send too little, the noise overwhelms the signal, if you will. And then the receiver power is based on the amount of power launched into the fiber by the transmitter and the amount of loss over the fiber, the amount of signal that's lost due to attenuation over the length of the fiber. So all that is going to factor into the link, if you will, the quality of the link, if you will. And here is, we have bit rates and so forth. This is some of the stuff we'll be measuring later this semester. When I start dealing with types of fibers, actually, we're going to come back in the next podcast and do that one.